So good afternoon, everyone. Good afternoon, everyone. So we will basically continue our discussions on the week 12 content. So the problems we have already solved for assignment 12. So this lecture will only be regarding the rest of the theory that was discussed in the week 12, basically your deregulated power systems and your unit commitment. So we'll just briefly see those concepts today. So last class we discussed that how the vertically integrated utility was changing under the scenario of deregulation. So we'll see how basically this works for using a small example. So let's say this is your area 1 with two GENCOs, GENCO 1 and GENCO 2, and two DISCOs, DISCO 1 and DISCO 2. Similarly, in the area 2, we have GENCO 3-4 and DISCO 3-4, and these two areas they are connected with a tie line here. So we'll see this DISCO participation matrix here. So let us just uh, fill this value for the contract participation factor. So this what basically this contract participation factor signifies that it is let's say this is your first position, right? 1 1. So it signifies that how much amount of its required power disco 1 is contracting from generator 1. Similarly, for this position, for this is your CPF 11. This is telling that how much disco 1 is contracting from genco 1. So this is your 2 1. So this is a CPF 2 1 will basically represent the amount of power disco 1 is contracting from genco 2. Similarly, CPF 3 1 and CPF 4 1. So basically these all represent, this first column will represent how much amount of power DISCO 1 is contracting from GENCO 1, 2, 3 and 4. So basically so yeah, basically this is the summation of this column 1, that is your CPF 11 plus CPF 21 plus CPF 31 plus CPF 41 is nothing but 1. Right, because this participation factor basically should add up to 1 so that the complete load of this disco 1 is satisfied. So if we write it in, so let the disco 1 load be basically 100, or it be in generalized form, let it be P1. So basically CPF 11 into P1 So we'll see it in example. Let's say let us basically fill this matrix here with actual values. So similarly for disco 2, 3 and 4 also. So let's say here it is contracting some point 2, point 2. It can be 0 also, right? So zero point 0.6. So here you can see it is summing to 1. Similarly here let's say it is 0.3, 0.1, 0.5, then 0.1. Here let's say it is 0, 0.5, 0.2, 0.3. This will be 0.4, this will be 0, this will be 0.3, this will be 0.2. So this will be 0.3. So you can see each column it is adding up to 1. Right. And let us take some data. So let the load demand of disco 1, 2, 3, 4 be, let's say 20, 40, 40 and 30 megawatt respectively. This is given, right? So this is a data for you. So from here we can calculate the power generated by each Genco. So how we will do that? Basically, so power generated or contracted by each by Genco 1, let us see first. So for Genco 1, so Disco 1 is your contract participation factor is point 0.2. Point 0.2 of how much? Of total capacity of Disco 1, right? So point 0.2 of 20. Similarly, basically this row, this row is the for the Genco 1. So for first disco, point 0.2 is the contract participation factor and the demand of disco 1 was 20. Similarly for uh, disco 2, so how much is the contract participation factor? So that will be 0.3 and its demand is 40, and for disco 3 it is 0. So 0 times 40 will be 0. Then disco 4 is contracting zero point 0.4 of its 30 megawatt. So this sum is the total power that will be generated by this Genco. So you can calculate this. Similarly for Genco 2, it will be, so let me copy this. Yeah, so point 0.2 of 20, point 0.1 of 40, and point 0.5 of 40, and 0 of 30. 20, 40, 40, 30. Yeah, point 0.2, point 0.1, point 0.5, 0. Yes. Similarly, for the third GENCO, it is 0 of 20, point 0.5 of 40, point 0.2 of 40, and point 0.3 of 30. Similarly, for your last GENCO 4, it is point 0.6 of 20, point 0.1 of 40, point 0.3 of 40, and point 0.3 of 30. So that will give the total power generated by each GENCO. So if you calculate this, so it will come around something 4 plus 1.2 plus 0 plus 1.2, that will be 6.4 megawatt. Similarly, for the second one, it will be 4 plus 4 plus 2, that is 10. So this is 0 and 2 and 8 and 9, that is 19. And for the last one, that will be okay. Yes, so for the last one, it will be 12 plus 4 plus 12 plus 9, so around 37. So let me just verify these values once. The first one is 28, second is 0.2, then 0.1, point 0.5, and the 0, 28. This is also 28. Then 0, 0.5, 0.2, and 0.3, 37. Here it is 0.6, 0.1, 0.3 and zero point 0.3. Yeah, 37. So this is the power generated by each disco basically. So can you just calculate the sum of or total power generated? That will be nothing but power generated by sum of power generated by each GENCO. Total power generated, that will be sum of above. So that is nothing but 130 megawatt. And here what was the total power demand by disco? That is nothing but sum of power demand of each disco was right, which was 20, 40, 40 and 30. So that is also equal to 130. So you can see that a power balance has been satisfied. That is, total power generated by the sum of GENCOs is exactly equal to the total power demand of each disco. So next thing what we would like to calculate is the tie line power flow. So can you, from these values, can you tell me what will be the tie line power flow between this area 1 to area 2? We have considered this. So that is nothing but, so let me take it to the next slide. So let me write this in consolidated form. By GENCO 1, 2, 3 and 4 is 28, 28, 37 and 37. So this is not required now. So what, for calculating the tie line power flow, first we need to calculate the total demand of discos in area 2. So what are the discos in area 2? That is 3 and 4, right? Area 2 from the GENCOs in area 1. From the GENCOs in area 1. So what are the GENCOs in area 1? They are G1 and G2, right? So we have to see first for disco 3. So disco 3, it is uh, taking no power from GENCO 1, and from GENCO 2 it is taking zero point 0.5 of 40. So this is for disco 3. What about disco 4? It is taking zero point 0.4 of its requirement from GENCO 1, and from GENCO 2 it is taking nothing. So is it clear? So basically we need to see this part, this transaction between disco 3 4, that is GENCO discos in area 2 and GENCOs in area 1. So this is this part. DISCO 3, 4 and GENCO 1, 2. So DISCO 3 is taking 0.5 of its demand, that is 40 from GENCO 2, and DISCO 4 is taking zero point 0.4 of 30 from GENCO 1. So that is 20 plus 12, 32, right? Yeah, so 32 megawatt. Next, we need to calculate the demand, total demand of DISCOs in area 1 from GENCOs in area 2. So which are the DISCOs in area 1? They are D1 and D2, and in area 2 the GENCOs are D3 and 4. So now we need to look for the transaction between D1, D2 and G3, G4. So this is this part of the matrix which I am highlighting here. So the DISCO 1 is taking 0.6 of its requirement, which is 0.6 of 20 from GENCO 4, and DISCO 4 is taking 0.5 of its requirement, which is 40 from GENCO 1, plus it is also taking zero point 0.1 of its requirement from GENCO 4. So that is nothing but 0.6 into 12 plus 0. This is 0.6 into 40 basically. So I think 36. Yeah. So that is 36 megawatt. So if you want to calculate the tie line power flow from area 1 to 2, so that will be nothing but this 32 minus 36, which gives it minus 4 megawatt, which means that for this case basically the power is flowing, or basically 4 megawatt of power flow from area 2 to area 1, because it is minus 1 minus 4 for 1 to 2, so from 2 to 1 it is plus 4. So I hope this part was clear, and how we calculate this tie line power flow. Next we will see, next topic was unit commitment, right? So yes, so what is this unit commitment? Basically uh, you have many generating units in your system, right? And each generating unit has its own fuel. So each generating station or generating unit or generating plant, generating unit has its own fuel cost characteristics. So what is this fuel cost characteristics? So it is nothing but the amount of fuel that will be, or fuel or raw material that is required by that generating unit to generate certain amount of power. So it is basically, this fuel cost characteristics is a quadratic function. So it is something like, if I write, so f of P, where P is the power generated in that plant, is something like A times P square plus B times P plus C. So if a generating unit has this type of fuel characteristics, it means that here, to generate for P amount of power, the cost that will be incurred by the generating unit is this F of P. So each unit has a different value of coefficients, different A, B, C, A, B, and C, depending upon the type of plant, type of unit, and various other factors. So that means that for generating the same 10 megawatt of power, different generating units, they will have different cost. So what we want to do is, we want to basically calculate the number of units to be committed, the number of units committed to satisfy our load with minimum operating cost. So here what we are trying to basically achieve is economic efficiency. So let's say you want to satisfy 10 megawatt of load and you have three generators. So you will decide that which generators you need to switch on depending upon their cost characteristics, such that the cost incurred is minimum. So it may so happen that only generator 1 can supply all the load, that may give the minimum cost, or the combination of them. So that calculation we do in unit commitment. So this is the objective. Apart from this, there are several complexities in this problem. So firstly, the first thing is that there is some startup and shutdown cost involved. So apart from this generating this fuel characteristics cost, you have to also consider the startup and shutdown cost involved for switching on or switching off the plant. So this startup cost basically, uh, it will depend, like you have the two type of startup cost, your hot start and cold start. So if your boiler is already hot, so generating power from that condition will require less amount of power. But if your boiler is cold, then you will require more steam to generate the power. So that is your involved in startup cost. And similarly for shutdown cost also, similar kind of things are there. So that all cost also you need to take care while calculating this unit commitment. But this startup cost and shutdown cost will only come once when it is switched on. So once it is switched on, after the it is being switched on, for the consequent time steps, uh, startup cost will not be there, only the operating cost will be there. because already you have switched on the unit. So only when the transition is from the startup cost, you need to consider only when you switch on a generating station which was off previously. So only when you go from off to on state, then this cost will come once. After that, once it is on, this cost will not come. Similarly, shutdown cost will be involved when you are switching, when you'll be switching on to off. Basically, when you are switching off a power plant which was previously on. So previously it was on and now you are switching it off. So for that time instant only this shutdown cost will come. So this additional cost you need to consider while calculating this operating cost in unit commitment. Apart from this, there are other constraints. So one thing is your minimum uptime and downtime. So minimum uptime and downtime. So what this means that once you switch, once a unit is switched on or off, switched on or off, it must remain in on or off state for its minimum up or downtime. So what this means is basically, let's say one plant was off at 10 a.m. and at 10 a.m. you're switching it on. And if its minimum uptown is, let's say, so at t equal to 10, you have switched on the unit. And let's say its minimum uptime is 2 hours. 2 hours is its minimum uptime. So it means that you can switch off this unit only after 12. So you switched on at 10 a.m. So you can switch it off only after 12 p.m. In between, you cannot switch it off at 11 p.m. even though you can get a minimum cost at that time, but still, due to this minimum uptime constraint, you cannot switch off this unit from between 10 a.m. to 2 p.m. Similarly, for downtime also, if it is switched off at 10 a.m., let's say, and its minimum downtime is somewhere around 2 hours, also same, let's take, then you cannot switch it on back before 12 p.m. So that is your minimum uptime and minimum downtime. And next constraint is your ramp up and down. So what this means is basically, let's say you have a power plant. Yeah, so I was talking about ramp up and ramp down. So basically, let's say you have a power plant whose minimum limit output is 0, and a maximum is, let's say, 50. And let's say at the current instant t equal to 1, it is generating at Pg equal to, let's say, 25. And additionally, let us consider that the ramp up of its generator is 5. So what this means that at t equal to 2, this generator, it can vary its output power, both, let's say, ramp up and down. Limits are 5 megawatt. So either it can go from maximum 25 to additional its ramp up limit plus its ramp up limit, and other, or it can decrease its power from Pg to its ramp down limit, which means that it can go from basically here, 50 plus 5, that is 55. No, it is at 25. So it can go till 30, or it can ramp down from 25 to 20. Means that t equal to 2, your Pg can vary between 20 to 30. So even if its maximum limit is 50, but due to the ramp up constraint, it can go only up to 30. And even if its minimum limit is 0, due to the ramp down constraint, it can go up to only 20 in the next time interval. So this constraint is known as your ramp up and down. Now, apart from this, uh, we have your reserves. Yes. So, reserve, you have two types of reserve. Basically, first we will discuss your static reserve. So, static reserve, it means that whenever there is a outage, because this generating units, they are plants basically, which are consist of different your turbine, valves, pumps, etc., boiler. Different units are there. So it may happen that sometimes some failure is taking place in the turbine. So you need to shut down that plant for certain time before it is repaired and brought into system back. So whenever there is a forced outage, so we calculate. You can mute yourself. You have joined. I am muting you. Okay. So whenever we calculate the probability of the forced outage in a year, and depending upon this forced outage, we calculate the amount of static reserve we need to keep, amount of static reserve to maintain or keep, what you can say, to maintain, so that the load is supplied throughout the year. Basically, we take the peak load here. Yeah. So depending upon, because if there is a outage means, let's say you have 100 megawatt of generation and 100 megawatt of load, and you have just committed 100 megawatt of generation only, and due to this forced outage, let's say 10 megawatt of your unit is shut down, so now you cannot meet 100 megawatt of load, right? So for that you need to keep this static reserve. That means for 100 megawatt of peak load, you need to have some percentage, let's say 110 or 120 megawatt of generation with you, so that in such forced outage condition, your load can be supplied even when the unit is off. So that is your static reserve. Next type of reserve that we keep is your spinning reserve. So spinning reserve is for shorter time interval. The static reserve we generally compute through for the year. Spinning reserve is basically before your 24 hours, day ahead that we say. Before the day, you need to plan how much amount of spinning reserve that you want to keep. So spinning reserve we keep to take care of the contingency that is taking place. Contingency, or these are the random outage that take place. So for this contingency, we calculate the possible contingency that may happen. We calculate the reserve required to handle the system load under different contingency scenarios. So for contingency scenarios, mostly we take for your generators and your transformers and your transmission lines. So these are the certain components which may fail. So how this reserve is calculated is basically, what you do is, let's say you have your 3 generator and 5 lines with you. This is for this. So for first contingency C1, you consider that there is a generator outage. Let's say G1 is not there. So you calculate how the system will operate only with G2, G3 and your 5 lines. And to operate under this contingency, how much amount of your spinning reserve you require. So that is your, let's say, SR1. Let, let us consider then another contingency we will consider, where let's say now your G2 is out under outage, under random outage. So basically now you have with you G1, G3 and your 5 lines. And let's say the reserve required to handle this contingency is your SR2. And similarly, for the third contingency scenario, let's say your third generator is under outage. So you have to calculate the spinning reserve considering G1, G2 and your 5 lines. that is your SR3. Similarly, now we have just considered only the outage of a generator. Next, we will consider when there is a outage of line. So for contingency C4, so all your generators are there, G1, G2, G3, but one of the lines is under outage. So you have only L1, L2, L3 and L4, and let's say line 5 is under outage, and under this scenario let the spinning reserve require be SR4. So similarly we'll calculate when there is a contingency for line 4, 3, 2 and 1, so that, and each case we'll calculate the spinning reserve. So the total or spinning reserve final that you keep for this system is the maximum of the spinning reserve required in each scenario. So maximum of SR1, 2, 3, 4, etc. up to SRN. What will be N here? Basically 8, because you have 8 components, right? 3 generator, 5 lines. So one contingency at a time. So total 8 contingency will be there. So you keep the final spinning reserve as the maximum of all these 8, so that your system can function smoothly under any contingency that is taking place. So this type of contingency scenarios are called as your n minus 1, because here out of n components, that is 8 components, at a time only you are considering that one component can fail. So that is your n minus 1 criteria that we tell. So spinning reserve, this is a special type. So the word spinning here, it indicates that this spinning reserve are basically from the generators which are already synchronized with the grid, are from units already spinning, that we say basically synchronized with grid, and they are ready to generate, because these are emergency scenarios. So if they are not synchronized means there will be time involved for getting ready, right, to the startup time basically. So to avoid that, the spinning reserves are those where the units are ready to generate power and they are already in synchronism with the grid. So that is your spinning reserve. So these are some of the constraints which we need to keep in mind while undergoing this unit commitment problem. Due to this, this is a very complex type of problem that we solve. So there are various methods for it, and in the class, I think dynamic programming has been explained by Professor Das, and I hope that was clear to you all. So I just explained what are the complexities involved in this problem. So you can imagine that it is not possible to solve in the class. And dynamic programming is one of the simplest method, which has explained here. So next thing that was taught was reliability. So reliability means that whatever result that you get from your unit commitment, so it should be such that the voltage the voltage frequency should be maintained always. But these are, as I said, these are plants which can have wear and tear. So, depending upon the type of the plant, we can draw the characteristics of the plant with respect to time, like this. So, with respect to time, and this is the state. So, 0 means it is off, 1 means it is on. So, this was your uptime for this much amount of period. Your plant was generating power. This is also another type, uptime 1, uptime 2, and uptime 3. This is your downtime, downtime 1, downtime 2, downtime 3. So for this much amount of period your unit was off. So reason for your switching off, so that may depend upon your maybe for maintenance issues you may shut down your plant, and likewise. So basically here we calculate the total uptime as summation of this individual uptime. So your uptime 1 plus 2 plus 3 divided by the total cycle. So in total cycle, it will be basically uptime 1, downtime 1, uptime 2, downtime 2, uptime 3, downtime 3. So that is your total cycle. So this is your uptime. Similarly, for downtime, that will be summation of your total downtime, that is D1, D2, D3 divided by total cycle. So from here we calculate the mean cycle time as this, your T up plus T down. Okay. From here another we calculate the failure rate, that is so it is the time how for which the unit is under failure. So that is nothing but 1 by the time for which it was on, that is T up. So that we denote by lambda, and repair rate, so that we denote by mu, which is nothing but your 1 by downtime. So also from here we can calculate the probability of the unit being in up state. So that is nothing but your uptime divided by up plus down, right? So that is nothing but you'll get it as mu by mu plus lambda. Similarly, downtime you can calculate as downtime by the probability of down be downtime by T up plus T down, that is lambda by lambda plus mu. So apart from this, another thing that was taught you was security constrained optimal unit commitment. So in the security constrained optimal unit commitment. So here basically you calculate some uh, insecurity level, and it should be less than your maximum allowed or maximum tolerated insecurity level. So your basically depend on this uptime and downtime, you calculate that for the probability that the system may fail to operate, and that probability should be less than your maximum tolerated insecurity level. So that was, I think, all for this week content. So I hope it was clear to all of you. And if you have any doubt, you can ask, or I think we'll close the session for this. So this was the last lecture for this Power System Engineering NPTEL course, and we are at the end here. So if you have any queries, you can ask. Otherwise, we'll close the session for today. Okay, I am then stopping this.